testing electronics systems. Today we are going to start looking at some of the measurement devices, and the first one is LRC meters. As you know, L stands for inductance, R is the resistance, and C is capacitance. So LRC meters, they are meters that are used for measuring inductance, capacitance, and resistance of electronics components. And they are of two types. Basically, the simpler ones, what they can do is to give you the impedance of that component on that test. Then you are the one that will now calculate either the the capacitance or inductance. Because we can remember the capacitive reactance is equal to 1 over 2 pi FC, and the inductive reactance is equal to 2 pi FL. So if you know the reactance, frequency of operation, you know it. 2 pi is a constant. You can find either your L or your C depending on the components. And the second type, they are the sophisticated ones, which can be used for measuring the actual value of the inductance or the actual value of the capacitance. In addition to this, they can also give you the value of series resistance of a particular capacitor, and of course they can give you the Q factor, which is the quality factor of a of an inductive component. You know, the inductive component is made using a wire which is turns, it is winded into a coil, and of course this inductance will have some percentage or some element of resistance in addition to the pure inductance. So the LRC meters, we have different types of them in use. That's the first one is a bridge method, and this one, as the name implies, it uses the Wheatstone bridge. And as you know, the Wheatstone bridge uses 4 components. In our secondary school physics, we know they are all resistors 1, 2, 3, 4, and one of them is the one whose resistance is to be determined, while the other 3, they are variable. You can be adjusting them until no current passes through your galvanometer, which is at the center of the bridge. So at this type of a bridge method, at the balance point, the bridge components, they are used in such a way that you know the values of the 3 components, and the last one is our device on that test, whose value of either inductance or capacitance is going to be determined. And of course, this method is suitable in applications where the frequencies are very low. Any frequency about 100 kilohertz or so is called a low frequency in this orientation, and they are the ones that use bridge methods. Now let us look at this bridge method. As I told you, the meter or the bridge connection is just like a Wheatstone bridge we know in our secondary school physics. Here you can see I have inductance or impedance Z1, Z2, and this is supposed to be Z3. This is a mistake. And this ZU is the impedance of the device on the test. So whenever you try to use this one, you can see that we have a meter M which is crossing the bridge, and this is my source of the energy that will power the all bridge circuit. And the component on that test, I told you, its impedance is given by ZU, while Z2 and Z3, that 4 is supposed to be 3, as I said. They are fixed values, we know them. And the Z1 is a variable impedance component. You can keep on either increasing its value or reducing its value until you reach a balance point where 0 deflection is noticed from this meter. And when that happens, you see that this equation becomes true. That is ZU, the impedance of the component on that test, is equal to Z3 over Z2 times Z1. I told you 2 and 3 are constant, while Z1 is a variable, and this variable, wherever you set it to get the balance point, you can know its value also. So we can see invariably Z1, Z2, and Z3, they are components whose impedances are known, and if you substitute this in this equation, you can get the impedance of the device on that test, which is your Z2. And in this case, you can use the formula for either inductive reactance or capacitive reactance in order to find the actual value of your inductor in case of inductor, or the actual value of your capacitor if it is a capacitive component. So the second method is what we call the current voltage measurement procedure, and this one is used for frequencies which are higher than the other one. We said the other one is around 100 kilohertz and below, but whenever you have a frequency beyond that, that bridge method, Wheatstone bridge method, will not serve the purpose because it cannot give you accurate measurement. So in this case, we use current voltage where the frequency is very high, and this method is known as RF-IV measurement method. RF means radio frequency. We are now assuming that any frequency that is higher than the other 100 kilohertz, we categorize it as radio frequency, and of course the IV stands for the measurement of current and the voltage. Now at this point, as I told you, since the frequency are very high, then it is used in impedance matched measurement system. The impedance matching, as you know, is a process of making sure that total or the highest power is transferred from the source to the load when there is match of their impedances. And of course, even this RFIV method, it is of two types, and these two types depend on the placement of the voltmeter and the current meter respectively. The first one, where we have our current meter coming first next to the source, then followed by our voltmeter. You can remember that for you to measure current, you put it in series, and for you to measure the voltage, you put it in parallel. So this one is suitable for the low impedance measurements, and the other one is for the high impedance measurement. And how do we use it? As I told you, all you need to do when you on your supply, you now take the reading of the current and the corresponding reading of the voltage. And if you have these two, you can see using ohms meter, the impedance of this device on that test is equal to voltage over current. Now if you divide the two, it will give you the impedance. And using the formula for either capacitive reactance or inductive reactance, you can subsequently find the value of the inductor or the capacitor, as the case may be. The difference between this one, which we said we use it for low impedance, and the other one, which is used for high impedance, is just the positioning of the current meter and the voltmeter. In this one, you can see that the current meter comes first, followed by the voltmeter, but here reverse is the case. The voltmeter came first and then followed by the current meter. And in each case, all we need to do is to get the current and get the corresponding voltage and use the Ohm's law to say the impedance is equal to V all over I. And if you know, if you find that value of impedance, you can translate it into either inductance or capacitance, depending on what you are measuring at the same time at that time. And also, if you want to get more accurate result, you have to use what we call the phase sensitive detector. This is a device that will be used for obtaining the phase angle between the voltage and the current. So the moment you get that, it can help you after knowing the impedance and also know the phase angle between the current and the voltage. Then you can use the complex analysis to convert it into either pure inductance or into capacitance, depending on whether you are measuring inductor or a capacitor. And of course, as I told you, all we need to do is to divide the voltage and the current to get the impedance. Together with this phase angle, we can get a better result. And I told you this impedance is in form of either pure resistance or capacitance or inductance, as the case may be. So whenever you want to use this device for making measurements, there are some hints, there are some tips that you have to take into account for you to get accurate result. The first one is to make sure that the operation frequency is the actual value you are measuring. If the circuit or the source has a frequency of 200 kilohertz, you have to make sure and verify that it is 200 kilohertz. Because when it is different, less than that or higher than that, we have some stray effects that can introduce stray inductance or stray capacitance because the frequency value changes. So you have to make sure the frequency is at the set value. And the next one is to make sure the amplitude of your signal source is exactly at that value, because whenever there is increase in that amplitude or there is decrease, definitely there is a stray component of either capacitance or inductance introduced into the circuit. And if that happens, definitely the result will never be completely accurate. And the tip number 3 is to make sure that the length of your lead, that is the length of the probes that you can be touching the point in order to get either the current or the voltage, the length doesn't reduce or doesn't increase. Because whenever you are operating at a very high frequency, which is above 1 megahertz in this case, the length of your probe's leads has effects. It is estimated that 10 nanohenry of inductance is introduced by any increase of 1 centimeter of the leads, that is the length of the probes. So you have to make sure they are at the designed value, they are not beyond or below the actual designed value. If not, they will introduce stray inductance in particular. The last hint is to make sure that you discharge your capacitors before you take any measurement in them, because some capacitors do store some charges inside them. We call this one a residual charge, and if it is present, definitely the value of the capacitance to be measured is going to be different, because the signal is what the source supply plus the residual inside that capacitance. So this is so far about the LRC meters. Now the next thing is we look at another measurement device, which we call. So we now look at signature analyzer, and this measurement instrument is used for checking data on different nodes, that is different points within any logic system. Example, if you have a microprocessor, it has different terminals. So if you want to check and see whether the data that is supposed to be there is the one being obtained or not, you use a signature analyzer. And this signature analyzer, it is used for different operation scenarios. For instance, you can put it in a test mode, that is to find whether the signal expected at a particular point is there or not. And of course, this measurement or this monitoring can be done at different points of any digital system. How this signature analyzer works is that it converts the serial data it will collect from that point, from that node, into equivalent hexadecimal data, and it has 4-digit length, although there are some that are different, more than the 4-digit, but the most common is the one we are going to be discussing now, and it has a 4-digit length. And how this signature analyzer works is that you connect the probes at a particular point under the test, that is the node that you want to check its function, and if you do that, it will be taking the data coming out from that node when it is activated by a clock, because the system, or most of the digital systems, they are synchronous in nature, that is, they are being operated using a single clock. So when you place your probes at the particular node, you press the start button, and that will select the edge of the point you want to start taking the signal. Is it the rising edge of the digital signal or the falling edge? It is selected using the start button, and when the number of beats have been taken, you now press the stop button, which will also select the edge at which the reading should stop. That is either the rising or falling. That is what we call the positive edge and the negative edge. And the pulses, the beats taken, they are passed through a shift register, which now go to the converting element of the signature analyzer, and it will now convert it into hexadecimal equivalent, as we have said. This is the block diagram of a typical signature analyzer. If you look at this terminal, is the clock. It is the one that drives the input control circuitry, and of course the shift register, which changes the serial bits taken into 4-bit hexadecimal. And here I have a terminal where we press a button to command the circuit to start taking the reading, and the one below it is to stop taking the readings. Now whatever is taken from this point, it has to put through a threshold circuit. Its function is to make sure that the signal for 1 or 0 is within the range of defined voltage. Now if this signature is captured correctly, then it indicates that the point which we are taking our measurement is operating normally, and if not, then we know that it is faulty. And where do we get the standard data that we should compare with? This standard data, they normally come with the repair manual, or sometimes from the service manuals of that particular digital system which you are analyzing using the signature analyzer. And this signature analyzer, it has a front panel like this, and this displays different inputs, different outputs, and of course the point at which the hexadecimal output is displayed. You can see that here we have an LED, and it stands for the gate. Whenever this LED is on, it means the gate is ready to start taking the pulses. And here is my LCD, that is liquid crystal display, where my 4-bit hexadecimal is displayed. And here I have another LED. Whenever it is on, it is telling you that the pulses or the bits you are taking from that particular node on that test, they are unstable, which automatically shows that it is not behaving, or it is not operating normally. And this is another LED. Whenever it is on, it is used for testing the probes. When you connect the two lights, that is the two probes of your measurement device, that is the signature analyzer, whenever this LED comes on, it means the probes are working normally. And down here we have another button line. It is the one that is used for turning on and turning off the signature analyzer, and of course it is a toggle switch. And this is the start. As I told you, it is used for telling this signature analyzer to start capturing the bits, and of course it is the one that selects either the positive edge or the negative edge, that is rising and the falling. The same thing with the stop, it is to stop the taking the bits. And the clock, as I told you, whenever you press it, you are now activating the overall system, because it is, as I told you, synchronous digital system. And this button, when you press it, you are saying that the data being displayed on the LCD should remain constant and stop taking any reading. And the last one, if you press it, it is turning the signature analyzer into self-test mode. It is now testing the analyzer itself to know whether it is functioning normally or there is some anomalies. So I have already explained what the gate is doing, is to indicate whether the gate is open to start capturing the data. The display is to give us our 4-bit hexadecimal. The unstable signature, whenever the LED is on, it is telling you that the signature you are capturing is unstable. Definitely the data will not be correct. The probe test, as I said, it is for testing the probes, that is the two terminals, the leads you place at any point to take the data, to make sure they are operating normally. And the line, as I told you, it is for switching on and off the signature analyzer. The starts and the stop, as I told you, they are used for selecting the edge at which to start capturing the data, either the positive edge or negative edge, which are rising and falling edge. And the hold, as I told you, is to hold the displayed 4-bit hexadecimal at the LCD or on the LCD, regardless of what is happening inside the system. And the self-test, as I told you, is to check the operation of the instrument itself, that's the signature analyzer to know whether it is functioning normally or not. So the next one is another simple digital device, very simple. We call it logic probe, and this logic probe, it gives us simple indication of the logic at a particular point in any digital system. If you use this tape, this is our lead, this is our probe. If you place it at a particular point, it can use LED to tell you whether the signal is high or low. It can even tell you that whether the system is operating or it is not operating. And of course, it is used for indicating the past changing pulses, that is unstable digital signal. Now, as you can see, we have only one probe, and this one probe is connected to the main body of the logic probe, and along this side we have LEDs, one to indicate logic 1, the other one to indicate logic 0, the other one to indicate pulses, past changing digital signals, and the other one, the last one, to show that the system is completely off, it is not taking any reading. Now, as I said, it can give us up to 4 different indications. The first one is the logic high, and it is indicated using a red color LED. The second one is the logic low, and it is indicated using green LED. The next one are the pulses, that is the unstable digital signal. It keeps on changing on and off at the pass rate. And the color of LED used is the amber. And of course, we have line tri-stated. This is the one that will tell us that the system is completely turned off and it is not indicating any signal. And of course, some of these logic probes, they have a point where you can select the family of the logic system you are testing, either TTL, that's transistor logic, or CMOS, that is complementary metal oxide semiconductor. And of course, the different families, they have different voltage levels. The voltage one, that is logic 1. The voltage for TTL and the CMOS are different. And the logic 0, that is low. It is also different from TTL to CMOS. Some logic probes sometimes do have an audible indication, that is they have a buzzer that will tell you that the signal has been captured, whether it is so high or low, or it is pulses, or even it is tri-stated. So this logic probe, as I told you, and as you can see, it is very simple device, and it has some advantages. The 2 advantages are the low cost and ease of use. The disadvantages is that the measurement is very rough, it cannot give you some detail, and of course the display is very poor because it is using only LED. Now, this logic probe, it has some specifications. Though we have said that it is used for just indication using LEDs, but nevertheless it is very important. It can show you whether the point has a problem or it is normal. And of course, the basic specifications of this logic probes are given on this table. The first one is the range of voltages for high signal logic 1. The value for TTL is given, and the value of CMOS is given. The next one is the value of voltages for the logic low, for TTL, and the CMOS. And of course, the supply voltage range is from 5 to 15, but the maximum it can withstand is 20 volts. And the frequency it can operate is maximum is 20 megahertz. And of course, the highest impedance is 1 mega ohm, and the smallest time it will take to identify the signal, high, low, tri-stated, or whatsoever, is 30 nanoseconds. So this is the end of this lecture number 2. As I always say, try to read and read again until you master the content. Thank you very much. Until we meet during our next lecture. Before then, I believe you are going to dedicate your time to watch and watch again. Thank you.